Okay, we're back. Now our job is to look at free body diagrams for systems in which there are two objects with mass that are both moving in some sort of linked fashion. This is not in the Regents Physics curriculum, this is strictly in the AP Physics 1 curriculum, although there is a lab or two that we do in Regents that kind of touches upon this, but it's not a focus. The prompt is as follows. A mass M1 resting on a frictionless table is attached to a string. The string passes over a frictionless pulley and is attached to a second mass M2 that is hanging in midair. Picture of the system is included below. And instead of just saying frictionless, it's actually important that we write frictionless and massless. I should have had that in there. What that means is we don't have to worry about the pulley at all. We are not concerned with that. The only things that we're concerned with are M1, the string connecting it, M1, and then M2. Okay, so M1, M2, and the string connecting them. We want to know, if the system is left alone, determine the acceleration of M2, the hanging mass, in terms of M1, M2, and G. Now, the in terms of is something that trips people up sometimes. What this means is that the only variables allowed in your answer are M1, M2, and G. Now, at the outset, you might be thinking like, well, that has nothing to do with forces, that has nothing to do with, it seems like it's not enough information or not enough to be able to write a solution. I promise you that it is, and this is going to work on, by solving for this, we're working on deriving equations, okay? Writing an equation for some measurable, for some quantity that is dependent on certain factors. When they say this, they are telling you that the acceleration is only going to be determined or dependent on M1, M2, and G. And it's our job to figure out how that equation looks by using the tools that we've used throughout this unit, by using free body diagrams and net force equations, and then using algebra to rearrange. There are some assumptions that are going to go into this that we're going to use for right now. The first one I kind of already said, assume frictionless massless pulley. In the future, we will work with pulleys that have mass, and that's probably a springtime topic, but that's a little bit more complex, and that's not what we're doing right now. Some of the other assumptions that we're going to make. The tension in our massless string is the same at all locations. What that means is that the tension in the string has the same value up here that it does down here, same magnitude, same size of tension. That doesn't mean the tension in the string can never change. It doesn't mean the tension in every string is always the same, or like in different strings is the same. What it means is just that at any instant in time, the tension here is the same as the tension here. That is one of the assumptions that we're going to make. Okay, pretty basic assumption. We're also going to assume that the string does not stretch. In other words, the string is not going to be acting like a spring. We're going to deal with non-stretchable strings. And probably the biggest assumption, and the easiest to make, is that the acceleration of one object is equal to the acceleration of the other object. And that goes right along with saying that the string does not stretch. In other words, if M2 accelerates, then M1 is going to accelerate at the same rate. Okay? Those are our basic assumptions, and with those, we can actually come up with a solution. Now, you'll notice that we have two objects here, M1 and M2. In the past, we've always only had one object. We're not going to do anything radically different here. We're just going to have two different free body diagrams. I'm going to start with M1. Our axis for M1, let's make it the standard axis, x, y, plus. The forces that act on M1 are as follows. There's a normal force upwards from the table that it's on. There is a tension force from the string that's pulling it to the right. And downwards, there is, of course, the force of gravity. But since there are two objects this time, I'm not just going to write Fg, I'm going to write Fg1 to make sure that we have it different from the force of gravity that will be on this object. And you'll notice also that I labeled my object M1 as well, because I'm going to have two different free body diagrams. You have to make sure you're labeling these correctly. This is why I harped so much on labeling your free body diagrams with what the object is, because you don't want to get confused about which object you're talking about. As far as M2 goes, I'm going to kind of reverse the order a little bit here. I'm going to draw M2. The forces on M2 are tension upwards this time. and the force of gravity on M2 downwards, and again, I'm going to call that FG2. I haven't drawn the axis in yet, and that's because the axis is going to look a little weird. I want you to think about this. If M1 moves in the positive x direction, what direction will M2 move in? If you said down, then you're correct, okay? If M1 moves, and then I'm not saying like you push M1 and then M2 stays there and the string kind of bunches up. I'm saying if you let the system move, M1 is going to move to the right, M2 is going to move down. Likewise, if you were to, we're not doing this, but if you were to pull the system to the left, if you pull M1 to the left, then M2 moves up. So you see that even though this motion is linked, okay, M1 moves right, that causes M2 to move, but it doesn't cause it to move right, it causes it to move down. However, as far as our axes go, we're going to say that that's the same direction because it makes the math so much easier, okay? Makes it so you just have to think about a little bit less in your head. Here's what our axis is going to look like. If M1 moves to the right, M2 moves down, it's easiest to say that for each object, those are both the positive x direction. So for M2, we're actually going to make the positive x direction downwards, okay? Remember, there's nothing that says your x direction has to point to the left or to the right. It can point in any direction you want as long as you are consistent with it. Since we have different objects, we can actually tilt our axes in different directions. You might be asking about the positive y direction. Well, it is important that we maintain the same basic relationship between x and y. If y is 90 degrees counterclockwise from x over here, it's got to be 90 degrees counterclockwise from x over here, so now y points to the right. You can imagine that you've just kind of taken your x and y axis and you've rotated it this way because, again, M2 is moving down as M1 moves to the right. Drawing, just like all the rest of the forces units, drawing the free body diagram is often the hardest part. After this, you're just doing math, and it's not even that hard of math. It's math that you've learned a long time ago. Now that we've got the free body diagrams drawn, we can get to writing the net force equations. We need net force equations for each object in each direction. Need net force equations for both objects in both directions. So I'm going to separate them. We're going to go with object number 1 over here. In the y direction, I like starting off with the y direction for some reason. F net y equals Fn minus Fg1, make sure you write the 1, equals M1 AY. Since we have two different masses, you have to specify which mass you're talking about. If you don't, I will take off points. M1 is very clearly not going to suddenly lift off of the surface of the table or sink down into it. I think that means that we can say safely that the acceleration is 0, and therefore the normal force is equal to M1 times g. In the x direction, the only force is tension, so that must be equal to M1 times AY. The net force in the x direction for object 1 is just the tension. Let's move to object number 2. This object has no forces in the y direction. Remember, the y direction is left and right here because we rotated our axis. So F net y equals 0 newtons, but F net x, and again be careful here, the positive x direction is down. That means this is the positive force, this is the negative force. So we write that like this, Fg2 minus t equals M2 AY. Now you might be asking, why haven't I written AY1 and AY2? Let's go back up to the third assumption. The acceleration of one object is equal to the acceleration of the other object. In other words, the entire system should always have the same exact acceleration throughout. I'm going to work with this equation a little bit. I can turn Fg2 into M2g, since Fg is just the force of gravity, and this is the force of gravity on object number 2, so it's M2 times g, minus the tension. You'll notice that tension is not one of the variables that I'm allowed to have in my equation. However, I do have another equation in which I solved for the tension over here. I found that the tension is equal to M1 AY, and we said that the tension in this massless string is the same at all locations. So this T is the same as this T. That means I can plug in the equation for T over here. Watch how that works. Since tension is equal to m1ay, that's all I'm going to turn this T into. m1ay equals m2ay. Why am I writing a y? I should be writing x for all these. I am so sorry. These are all accelerations in the x direction. So I apologize for what I've been saying. It has been complete nonsense. But you're probably used to that by now. I want to solve for the acceleration of m2 in the x direction. That means since I have m2g minus m1ax equals m2ax, I need to get the ax's on the same side. I'm going to add m1ax to the other side, and I'm actually going to do another step right at that same spot since I have ax in both terms. I'm going to take ax out and write this as m1 plus m2ax. So I've just done two steps there. I've added m1ax to the other side, and then I took ax out, and what I'm left with is m1 plus m2. Remember, if I redistributed this to both sides, or to both terms, it would be m1ax plus m2ax. Okay, this is totally legal to do. Then I just divide m1 plus m2 to the other side, and I end up with ax equals m2g over m1 plus m2. And that is the acceleration of this system if I just let it go, or if we just let it go. You'll notice that since we substituted in the equation for tension, the t just kind of goes away because we plugged in a different equation that we know is equal to t. The acceleration is not dependent on the tension at all. And this is because the tension is what we would call an internal force. Okay? The net force on an object or a system depends on the net forces that originate from outside that system. My system here, okay, remember a system is a collection of objects. My system here is m1, m2, and the string. Tension is within that system. There is tension between m1 and the string, and there is tension between m2 and the string. Okay, that's inside the system. The other forces that I listed here, the normal force, that's the force from the table on m1. That's an external force. Force of gravity, that's the force between Earth and m1, or Earth and m2. That is an external force. External forces contribute to the acceleration of the system. Internal forces do not. So since tension is an internal force, it doesn't affect the net force or acceleration of or on the system. That's very important to understand. Okay? Internal forces have no effect on the overall system. There's a few things I want to point out before we go to our next example. First thing is I want you to look at the form of this equation. Now, no one is going to guess this without training off the top of their head, okay? I would not have guessed that this is what the equation for the acceleration boils down to. But let's take a closer look at it and see if we can't kind of figure out some meaning from this. m2g is on the top. Think about what m2g is. If I were to look, okay, so the mass of the second object times g, that's just the weight or the force of gravity on the second object, this one right here. And if you look, that's the force that's driving this whole entire motion. If you were to get rid of this force somehow, well, you wouldn't need the tension, and that means m1 would just kind of stay there, and m2 would just kind of stay there. So, well, I mean, really what that would mean is m2 doesn't even exist anymore. The force of gravity on object number 2 is what drives the entire system forward. In other words, it's basically the net force on our system as a whole in the x direction. And that makes sense because if we're talking about net force on a system, like we just got done saying, the tension is an internal force for the system, therefore it doesn't affect the net force on the system. So interestingly, the top is the force of gravity on m2. Force of gravity on m2. And what that really is, in this case, is the net external force. External meaning it originates from outside of the system. What about the bottom, m1 plus m2? If you think about it for a second, that's just the total mass. So what we've got here is an expression for the net external force, the net force, over the mass. If you take the net force and divide by mass, you get the acceleration. This equation is just a restatement of Newton's second law. It makes total sense. The last thing I want to look at here is a topic called limiting factors. Limiting factors are a little, I don't want to say tricky, but they can, so limits are a pre-calculus or calculus topic. If you haven't done them yet, that's not a big deal. They're actually pretty easy, especially in this context. The way we talk about a limit is we look at what happens if we make some factor here go either to 0 or go to infinity, and we imagine, okay, what does the math say that would happen, and what does what would happen in real life? What do we think would happen without necessarily thinking about the math? So here's how we write it. Let's take the limit as m1 goes to infinity. So basically, what happens if we make m1 really, really, really big? Well, let's think about it from a experimental perspective. If you make m1 really big, then that's increasing the mass of the system. It's going to make it so that the string has to pull very, very, very hard on m1 just to get it to move anywhere. Well, m2 has a limited driving, force that's trying to accelerate it down. Okay, it's got a force m2g, the force of gravity on it, that's causing the acceleration down. That force isn't going to get any bigger just because m1 gets bigger. So interestingly, if you make m1 really, really big, it's going to be much, much harder for this system to accelerate. You might expect the acceleration to start to decrease. Let's look at the math here. Let's look at the equation for the acceleration and see if that makes sense given the equation. If m1 gets really, really, really big, then basically the bottom of this is going to start to go to infinity, right? It's going to get really, really, really big. But that's not changing the top at all. The top is still going to be m2g, so we're going to have this number over something that's really, really, really big. And as m1 gets bigger and bigger and bigger, this fraction is going to get smaller and smaller and smaller until it approaches, but never quite hits, an acceleration of 0 meters per second squared. That's exactly what we just said. The bigger m1 gets, the harder it is for the system to accelerate. So in this case, the limit seems to make sense. We look at these limiting cases to make sure that our equation matches what we think should really happen in real life. We can do the same thing for what happens if m2 goes to infinity. If m2 goes to infinity, then that means, let's look at it from a practical perspective first, then m2, is going to get bigger and bigger and bigger, and basically, it's not really going to matter what m1 is, okay? Because the m1, which is helping to cause the tension in the string, that tension is not going to be nearly as big as the force of gravity on m2. So it's almost like m1 starts to matter less and less and less. So as m2 gets bigger, okay, as m2 gets bigger, it's going to fall down even more easily. It's going to be able to overcome that force from the tension from that string even more easily. Now, this doesn't mean that it's going to fall infinitely fast, because we know that objects that have no forces on them other than gravity fall at a rate of 10 meters per second squared. That's their acceleration. So as this object gets bigger and bigger and bigger, m1 just starts to matter less and less. There's a smaller and smaller, relatively, force acting on m2. So what that means is this object should start to fall at approximately a rate of 10 meters per second squared. Let's see if that happens when we look at the math. If m2 gets really big, if it goes towards infinity, the top goes towards infinity. If the bottom gets really big, this is a little trickier, the bottom also goes towards infinity. But if you think about it, if m2 gets really big compared to m1, it's almost like m1 isn't even there. So it's almost like this becomes m2g over just m2, if m2 is sufficiently big. And what can we do with those m2s? We could actually cancel those out, and look what we get. The limit as m2 gets really big approximately is g. It starts to have an acceleration that's about equal to g. We can do this in the lab. We can actually see this happen in the lab. We will never get an acceleration that's bigger than g, because this object basically just ends up being in free fall. So I just wanted to point out that we can do this limiting case analysis, and this is a very common AP question. What happens when you make this one object much heavier than the other? What happens if you make this object much lighter than the other? That's a very common AP question, and one that you should be prepared for. Now we're going to go to a slightly different example. It's pretty much the same thing, but now we repeat the experiment on a table that is not frictionless. The coefficient of kinetic friction between the table and M1 is mu. We're going to determine the acceleration of M1 in terms of M1, M2, mu, and g. All the same assumptions still apply. We have to make our free body diagrams first. Remember, since there's two objects, there's going to be two of them. So we're going to have M1. That's going to experience a force of tension in that direction. It's going to experience a normal force in this direction. It's going to experience a force of friction in this direction. And it's going to experience a force of gravity in this direction, Fg1. And I totally forgot to put an axis on it. So now we have our axis. Positive x direction, that's tension. Normal force is in the positive y direction. Force of friction is in the negative x direction. Force of gravity on object number 1 is in the negative y direction. For my other object, it's the exact same free body diagram as before. Remember to tilt your axis so that you line up the directions that the objects are moving in. So this is the x direction, this is the y direction. We've got tension pointing up, force of gravity on object number 2 pointing down. We need separate free body diagrams for each object. For object number 1, in the y direction, we have Fn minus Fg1 equals m1ay. Since there is no acceleration in the y direction, m1 is not about to accelerate in either y direction, positive or negative. That's 0. Fn ends up being m1g. In the x direction, we have tension minus the force of friction equals m1ax. And since we're assuming that this system is moving, okay, because we're trying to calculate the acceleration, this means that this force of friction is kinetic friction, which means we can write this as T minus mu Fn equals m1ax. Sometimes there's a k on that to show that it's mu k, kinetic friction, but we don't have that here. That's fine. We just solved for Fn, so we could even write this as T minus mu m1g, because Fn is equal to m1g, equals m1ax. Let's go over to object 2 in the y direction. F net y is 0 newtons. In the x direction, we have the same equation as before. Fg2, because that's in the positive x direction, minus the tension equals m2ax. And again, this is in the positive direction, this is in the negative direction, because that's how we set up our axis. You write the equations based on the forces and the axis. The axis is crucially important. So this turns into m2g minus t equals m2ax. We could, since we're looking for the acceleration, we're allowed to use mu, m1, m2, and g, but we're not allowed to use t. We need to solve one of these equations for t and then plug that into the other equation. That will cause the t to disappear in our final answer. This is just what you did. You probably learned this in 8th or 9th grade. I can do that easily over here by adding mu m1g to the other side. So t equals mu m1g plus m1ax. I'm going to take this, since this is equal to t, and I have a t over here, I'm going to plug this in here. And notice that there's a negative, so that's going to get distributed to both terms. m2g minus mu m1g minus m1ax equals m2ax. I want to get the ax's on one side, so I can pull them out. So this is going to become m2g minus mu m1g equals, so I'm going to bring m1ax to the other side, and then I'm going to take out the ax just like last time. m1 plus m2ax. Divide it back to the other side. Ax is equal to m2g minus mu m1g over m1 plus m2. Again, a couple things to note. This equation right here, the expression on the top, m2g minus mu m1g, m2g is the force of gravity on object number 2. That's what's trying to drive the system to the right and down. There's a force trying to stop that, though. It's the force of friction. And we found that the force of friction can be written as mu times m1 times g. So this right here, the top, is really gravity, the force of gravity on m2 minus the force of friction on m1. Those are the external forces in the x direction. Once again, we still have the net external force here, and this, as it was last time, is the total mass. So again, we have net force over mass equals our acceleration. One quick note about this, it looks like you could actually get a negative acceleration if you made this term bigger than m2g, but that would be physically impossible. You wouldn't have a situation where you have this object, or where you have this system moving, moving, I guess, continuously, but there'd be acceleration to the left. What could happen, basically, is you would have enough. I guess if the system was in motion originally and was slowing down, you could have some acceleration to the left, but it wouldn't cause the objects to move to the left. It would just slow them down or stop them. Okay, so it does get a little, not dicey, but you do have to think a little bit about how big this term can get and still have the system continuously moving down and to the right. And there are scenarios actually where this gets so big that the system just doesn't move at all. It doesn't move organically. You would have to push it. And in that case, we would be dealing with static friction, though. Okay? Real quick, just right at the end, let's calculate how big the acceleration of m1 is, given some parameters. m1 is 8 kilograms, m2 is 5 kilograms, mu is 0.2. We take our equation for the acceleration. And we plug our numbers in. And one thing I want to note, sometimes people get really freaked out when they see equations like this and they think, how am I ever supposed to get to this? All you're doing is algebra. That's the limit of what you're doing, okay? You are only doing algebra. The real physics is in the free body diagrams and the writing of the net force equations. After that, it's just math. Math just requires practice, okay? Don't think that doing all this stuff down here, once you start rearranging, that's really not even physics. That's math, and that's math that you have been good at for a while. So the physics is in the analysis and the setting up of what this is going to be. Then we use math to get to a final answer. So if you're a little shaky on the math, okay, we can review that, okay? You have to be good at it, but we can review that, and that's pretty easy to do. The physics itself is really not all that hard. It's that sometimes people get a little hung up with the math. And also, don't think that this is something that you have to memorize, like these equations, okay? There's absolutely no reason to memorize an equation like this because it's very situation dependent. What you need to do instead, I don't really view it as memorizing. You need to learn the process that we're using to get here, okay? Writing the free body diagrams, drawing the free body diagrams correctly, writing the net force equations correctly, knowing the rules for those, and then doing some math. That's different from memorizing. Okay, so we're going to get 5 times 10, which is 50. 8 times 10 times 0.2 is 16. 50 minus 16 is 34. Divided by 8 plus 5 is 13. We end up with 2.62 meters per second squared is the acceleration. Okay, there is how to deal with with situations in which you have two objects that are moving together in some sort of system. We've got one more video to go. It is kind of a grab bag. We're going to talk a little bit about air resistance, which I know we've talked about before. We're also going to talk a little bit about center of mass in a very abstract sort of meaning. And that will be the last videos for the forces unit. We'll do those next time.